The Adjust Me Wrench by B&B Incorporated. What's Adjust Me, you ask? It's the ultimate of wrenches. Our team examined many wrenches available on the market, and all of them have problems. From corrosion issues to strength issues, or weighing as much as a brick. We found nothing good. We set out to design the best wrench while remaining affordable for our customers and to ensure it is the best available. So, how it's used. Adjustable wrenches have a wide range of uses, from repairing and assembling household objects to plumbing and automotive applications. Much of this can be attributed to the jaw adjusting to fit the size of different nuts and bolts. For the design and analysis of our adjustable wrench, various functional requirements and design specifications were discussed and finalized in order to obtain the desired qualities and characteristics. The functional requirements that the team created were that the wrench was to rotate nuts and bolts using a distance arm mechanism, and that it would be able to securely grip onto the wanted part with a worm screw mechanism. The design requirements for the adjustable wrench are as follows. The wrench should be able to withstand at least 20 years of intermediate service, while costing less than $5 in raw materials. It should also have a jaw width that should be at least 1 inch wide. It should not weigh more than 2 pounds, be able to resist various solvents and lubricants. The total length should be about 12 inches. Handle width should be 3/4 of an inch. The jaw thickness should be 0.5 inches. It should be able to withstand 500 pounds of force on the jaws. And it should be able to withstand a force of 100 pounds applied to the end of the wrench without deflecting more than 1 millimeter. And finally, it should have a Vickers hardness greater than 450.
To select the proper material, several considerations were taken into account. One major material selection process includes creating MPIs. Our team's objective was to minimize mass. With regards to our free variable of thickness, our team was able to relate relevant properties such as shear strength, deflection resistance, and cost per unit volume in order to create MPI graphs to refine our material selection process using CES EduPad. In order to simplify the design of the wrench, we have assumed the shape of the wrench to be made of a rectangular prism for a handle, right triangles for jaws, and a trapezoid for the head. After applying the mentioned constraints on our MPI graphs, the suitable metals included some cast and tool steels and high alloy steels. In order to further screen the properties of the materials, we considered additional relevant constraints such as service temperature, manufacturability in terms of current industrial practices, and toughness allows for the final filtering to select the proper material for our tool. The material we chose in the end is AC5160 alloy steel, with S17400 steel as a close second place due to its availability in North America. For more information, please take a look at the supporting document.
Our wrenches are manufactured using conventional manufacturing methods and a step-by-step process to ensure our wrenches meet the highest of standards. The process includes drop forging, stamping, normalizing, shot blasting, machining, heat treatment, chrome plating, and final assembly. The process of drop forming is a process in which steel blanks are formed into the shape of the wrench body. The forging is done at temperatures between 2100 and 2200 degrees Fahrenheit to allow for optimal stamping properties without affecting the microstructure greatly. The excess material that squeezes out of the die is then trimmed off. Once in the desired shape, the wrench body is ejected from the die and cooled down for further processing.
Going back to our chosen material of 5160 steel, there are several ways to achieve the required strength and heat treatment listed by our functional requirements. AC5160 steel is a high carbon and chromium steel that is most commonly used in the automotive field and heavy screwing applications and blade construction for its outstanding toughness and fatigue resistance. Assuming that the material arrives with no significant treatment, the strengthening process for 5160 steel includes normalization, quenching, then tempering. Normalization is the process of heating the steel above its recrystallization temperature of around 830 to 910 degrees Celsius. Similar to annealing, this temperature allows for the recovery of deformation energy, such as dendritic segregations, to move toward a more stable state. Once the metal reaches a more stable state, there is a reduction in dislocation density through the rearrangement of dislocations, also known as dislocation annihilation or polygonization. This rearrangement of dislocations thus promotes the nucleation and growth of strain-free grains within the microstructure. Finally, the metal is allowed to cool in the air until the material reaches room temperature. The normalization process usually takes 2 to 3 hours depending on the batch size and cooling rate, but can be repeated multiple times to control grain growth and residual stress reduction. This process is much more widely used compared to annealing due to its low cost and time requirements. Although annealing allows for a closer equilibrium composition and better residual stress reduction, the cost and time factor outweighs the benefits of annealing.
Following normalization, the wrenches undergo shot blasting. This is a process in which a high-pressure stream of aluminum oxide beads are sprayed at the wrench to deburr and clean the surface. The wrenches are then ground to give them smooth edges and further remove contaminants to allow for good adhesion during the plating process. Following shot blasting and grinding, there are then the stages of machining. The worm gear and wrench jaw are milled out of 5160 stock using a CNC. Channels are also milled in the wrench bodies to allow for the components to be assembled at a later point. High precision is required to ensure little movement in the system while allowing for smooth operation without binding.
After the shot blasting process, the metal is then preheated to austenitization temperature, around 850 degrees Celsius, in which the time is dependent on the thickness of the material. The quenching process can be controlled by using the time-temperature transformation diagram of 5160 steel. This diagram allows for an accurate prediction of the phase formed when cooling a specific steel at a temperature and time. For 5160 steel, a quenching process could include quenching the material from 850 degrees to 300 degrees for 5 minutes, followed by room temperature cooling. The quenching medium used is vegetable oil due to its property of extracting heat much slower than water, preventing excess stress formations which can lead to cracking. However, the hardening from using oil is less than of water due to the slower cooling rate. From this information, the graph tells us that slightly greater than 50% of the material's composition is made up of martensite. Specifically, plate martensite forms during quenching due to the steel's high carbon composition of 0.6%. This is important as plate martensite is very hard as its body-centered tetragonal crystal structure contains no close-packed slip planes on which dislocations can move easily. Furthermore, interstitial sites are occupied by carbon atoms which additionally restrict dislocation movement. Once quenched, the steel is extremely hard but very brittle. In order to restore some ductility, the hardened material must undergo tempering. Tempering of steel martensite can decompose to produce a new composition depending on the temperature. With regards to our functional requirements, the proper tempering temperature is 205 degrees Celsius for approximately an hour, which mainly produces stable alpha ferrite and cementite to increase ductility. The steel is then air-cooled and the process can then be repeated to produce the desired formability.
At this point, the wrench will then be chrome-plated in order to protect it from corrosion and to help increase durability under constant use of tightening and untightening nuts and bolts. The process of chrome plating involves applying a layer of chromium onto the wrench by electroplating. Essentially, both chromium and the wrenches will be dunked in a bath of chromic acid. When a current is passed through both the chromium and the wrenches, they become electrodes, while the chromic acid will become an electrolyte. During electrolysis, the wrench, which is the cathode, will become plated with chromium atoms from the chromium, which is the anode. This wrench will most likely be kept in a toolbox for most of its life, while on the occasion of being dropped or misused. Chrome plating will add a layer of hardness that will protect the steel from scratching or denting. This will improve the longevity of the wrench as the resistance to wear has significantly increased. The final step of manufacturing our high-quality wrenches is assembling and testing. The adjustable jaw is placed in the wrench body, and the worm gear is slid into place. The gear is then fixed in place using a pivot screw. Lastly, the wrench is tested to ensure smooth operation without binding, and all quality specifications are met. If you'd like to know any more information about our wrench, please refer to our supporting document.